Let's look at a detailed example now, which is the same one we took earlier, and we'll do this with some brute force. Okay, let's start the brute force by giving these vertices some names. V1, V2, V3. I won't name all of them, but I'll name all the edges. So suppose E1 is this edge and E2 is this one, E3 oriented accordingly, E4, E5, E6, E7, E8 and E9. Yeah. See why you don't want to be computing much by hand. You can, these are nice to put on a computer or something. Even then you would want something more efficient, but lots of them. So we can have a coefficient, right? So suppose we take C1. Yeah. So C1 is going to be sum I equals 1 to 9 AI and EI, where AI belongs to the ring which we'll take as Z here. Okay, and now suppose let's call this sigma. Okay, and so suppose boundary of sigma. Okay, and the boundary of sigma is going to be some B I Vi. I won't even count how many vertices. We'll say, let's say Bj Vj is 0. Okay, so then all coefficients Bj are 0. So let's see what that tells us here. Okay, if B2 is 0, the coefficient of this is 0. So the coefficient V2 comes twice. Okay, so what we know is that the boundary of, not I, but boundary of E1 is going to be V2 minus V1, and boundary of E2 is going to be V3 minus V2, and there are no other V2 terms. Okay, so what this tells you from here is that the coefficient of boundary of E1 is going to be, therefore, the coefficient of V2 is going to be A1 minus A2 is 0. So A1 equals A2. Let's say is alpha. I'll define this to be alpha. So suppose this guy is, so this coefficient is alpha. This coefficient is also alpha. What about E3? Now similarly we'll see that so this guy enters and this guy exits from here. Now what we'll see is that the sum of the coefficient of A3 and alpha is going to be 0 because of the coefficient of V1. So this has to be minus alpha because of matching here. Now what about at this vertex? We have an alpha from here, minus alpha from here, hence 0, and we have an A4 from here. So A4 is going to be equal to 0. Okay, we can go on. Now E5 and E6 have to be equal because you go in and here. So let's call this beta. And E7 and E8 have to be 0. So let's call this gamma. And what about E9? Well, E9 is going to be the following. So at this point we have a gamma, a beta, and an A9. So this is going to be minus of beta plus gamma. Okay, and therefore if you see the sum, sigma is going to be equal to alpha times the E1 plus E2 minus E3, and there's no coefficient of E4, plus beta times E5 plus E6, and then we can split off the E9, take one E9 here, and the other E9 will come in the coefficient of gamma. Okay, so the gamma will have an E7 plus E8 plus, so not plus, minus E9. And it's easy to see the boundary of each of these is 0. So boundary of E1 plus E2 minus E3 is going to have each of these vertices with coefficient 0. And the same goes with the boundary of beta and boundary of gamma. Okay, so Z1 equals, in fact, if we give these guys names, let's call this little z1, z2, and little z, or for consistency, let alpha, z beta, and z gamma. So you can see Z1 is going to be equal to alpha Z alpha plus beta Z beta plus gamma times Z gamma. And alpha, beta, gamma are now going to be arbitrary integers, because whatever integer you have, you can see this is this. But then Z1 is also equal to H1 because there is no C2. Okay. On the other hand, if I happen to fill up this region, okay, so I add a triangle here, then its boundary is going to be Z alpha. And so when I quotient it, I'm going to get just Z beta plus Z gamma. Okay. In a different context, we'll see an example where we have a C2 as well. But this was our first example of showing that we can actually calculate. It's a little bit painful, but it also illustrated our definitions. Not all of them, because we didn't calculate the image in any detail, but we illustrated some amount of our definitions.